afternoon. It's Friday. Partly cloudy in London, as you might expect. Another week has passed, and with it, the usual assortment of pronouncements and projections regarding artificial intelligence. One finds oneself reflecting on a rather prescient observation from Alan Turing himself. I've now got myself into the kind of trouble that I have always considered to be quite a possibility for me. No doubt I shall emerge from it all a different man, but quite who I've not found out. It's a sentiment that seems to resonate with the current climate, wouldn't you agree? A great deal of noise, a considerable amount of earnest pronouncement, and the perennial challenge of discerning the actual signal. That, as ever, is our aim here. To navigate the claims and counterclaims, and to identify what, if anything, is genuinely noteworthy. This is Turing's Torch, Artificial Intelligence Weekly, the bits that matter, minus the hype. We begin with something almost painfully simple. A team at a university put a tiny prompt into an artificial intelligence interface asking people to pause and reflect on energy use. The result was modest but detectable. Users sent fewer frivolous queries and avoidable compute dropped in the experiment. It sounds trivial because it is trivial. Yet trivial interventions can matter when multiplied across millions of interactions. What the experiment shows is not that prompts solve data center emissions overnight. It shows that some waste in artificial intelligence consumption is human, not purely architectural. People prod models the way they prod search engines, often without thinking about cost or consequence. A short message that reframes an interaction as consuming energy nudges some of that behavior. At scale, marginal reductions in calls and long chats add up to material savings in electricity and expense. The important follow-up is practical. Behavioral nudges buy time, but they do not replace engineering. Prompts will fatigue, and be clicked past. Some users will deliberately bypass them. Companies can display a thoughtful pop-up and then carry on with the same heavy, inefficient services. Effective climate strategy for artificial intelligence will combine nudges with stricter defaults, clearer metering, pricing that matches real cost, and better model efficiency. A banner on a screen is useful. Durable change needs hardware and policy. The framing of costs is relevant because the industry is making a broader shift toward metered economics. GitHub moved its coding assistant from a flat subscription to a tokenized model, and users found the new bills unpredictable within a day. Tokens are the unit models used to eat input and spit output. Longer prompts, more completions, and frequent experimentation all raise token consumption. Under a subscription you buy predictability, under metering you buy precision. That trade-off reshapes behavior. For engineers and small teams this change is immediate and practical. Suddenly experiments have a cost line you did not plan for. People throttle helpful but chatty features. Organizations build quotas, dashboards and approval flows to curtail surprises. The economic effect is not neutral. Large companies can smooth variance and negotiate discounts. Smaller firms cannot. Metered billing favors scale and negotiation power, and with scale comes control over who gets the best models for the cheapest price. The tension is visible inside large firms too. A major retailer rolled out an internal coding assistant for staff to experiment with, then quietly throttled access after usage exploded. The assistant runs on paid models. When thousands of employees start asking for code, drafts and diagnostics all day, infrastructure and cloud bills spike. The response was technical and managerial: limit users, introduce quotas, and buy time to build caching, batching and cheaper fallback models. The message is plain. Pilots do not scale for free. That mismatch between enthusiasm and capacity matters for governance as much as it does for bills. When you restrict access, you change workflows and training assumptions. Teams become unevenly empowered. People reach for public tools outside corporate controls. Those workarounds increase security and compliance risk. So the mundane actions of turning a feature on or off end up restructuring power inside an organization. When you put economics in the center, another business dynamic follows. Firms that are preparing to sell to enterprise customers are reshaping their product roadmaps around procurement expectations. One of the companies behind a well-known conversational model filed to go public, and the tone of its filing was instructive. The document read less like a research manifesto and more like a product pitch to procurement teams. An IPO reframes the goal: predictable revenue, defined SLAs, and compatibility with the sorts of audit and compliance checks purchasing departments insist upon. That shift matters to customers and to researchers. Enterprise buyers gain more predictable contracts and contractual remedies. They will demand uptime guarantees, patch cadences, and documentation you can audit. For researchers, the trade is less freedom to roll with experiments into a production cluster overnight. Releases become controlled and slow rather than impulsive. The market rewards reliability. The effect is both cultural and structural. Artificial intelligence services mature into products with vendor responsibilities and legal attachments. The commercialization trend reshapes competition too. Enterprise procurement privileges incumbents who can absorb certification costs and operational overhead. Startups without an enterprise-grade compliance story find it harder to compete. So the IPO market is not merely about public listings. It signals a transformation in market structure. Research units are becoming regulated suppliers, and that changes incentives accordingly. That same lesson shows up in utility and infrastructure projects. A major European energy firm moved its grid and business systems onto a single enterprise platform with the explicit aim of standardizing data for machine learning. The pitch was straightforward: consistent timestamps, unified asset registries, and a single source of truth make predictive maintenance and demand forecasting practical. In a grid crowded with rooftop solar, batteries and electric vehicles, consistency makes models usable rather than wishful. The work is prosaic. Data cleaning, schema alignment and governance are less glamorous than new model architectures. But they are the only way to get machine learning to act on operational decisions. Success is measured in avoided emergency repairs, fewer outages and deferred capital replacements. Those are boring but lucrative things for a regulated utility. They translate directly into cash flow and regulatory credibility. There is, of course, a countervailing risk. Centralizing critical operational data increases attack surface and vendor dependency. A single platform can become a single point of failure. Consolidation also concentrates bargaining power. Choosing a vendor is not merely a technical decision, it is a long-term political and economic one for any grid operator. Which brings us to another point that has been more visible this week: the shape of labor and responsibility inside artificial intelligence projects. Medical artificial intelligence highlights this clearly. The breakthroughs you read about are built on a far less glamorous foundation: exquisitely curated labels created by clinicians. Label quality in medicine is not tick-box work. It is grading severity, localizing pathology, and recording uncertainty in the way real clinicians do. Two experts will often disagree, and that disagreement is a feature of the data, not a mistake. If you train models on convenience labels instead of clinical judgments, you get tools that reproduce convenience. They perform in neat validation studies and fail in the busy clinic. The cost is not only patient safety, it is regulatory exposure, reputational damage, and the economic cost of redeployment. Hospitals and insurers are starting to demand provenance: who labeled what, under what protocol, and with what uncertainty. That turns data curation into clinical work. The wider point is that artificial intelligence often amplifies existing labor rather than replacing it. Small businesses are adopting models to do tasks they used to outsource. An owner can use a model to draft marketing, summarize feedback, or make invoices. But the output is only as useful as the prompts, the data connectors, and the oversight. Prompting is now part of jobs. Integration is part of jobs. The models change who provides value, not necessarily whether value is needed. That pattern repeats in enterprise engineering. Teams can prototype clever agents in hours, but production introduces messy plumbing, sandboxing, credentials, state management and robust error handling. Several providers have started packaging that plumbing into managed services. One of the industry offers integrates sandboxing, state tracking and credential handling so teams can deploy agents faster. The convenience is real. The trade is also real. You hand over secrets, trust someone else's sandboxing, and accept their recovery logic. In return you shortcut months of engineering. That trade-off is the familiar cloud bargain dressed in agent rhetoric. Managed services accelerate time to value but concentrate risk. For compliance-sensitive organizations, the managed route is an experiment, not a destination. Expect to use managed agents for pilots and then reintroduce bespoke engineering for critical systems. The same dynamic applies to tools that tidy up command line complexity. A cross-platform desktop application wrapped around an agent engine makes demos and testing accessible to non-engineers. Product managers and designers can now poke the agent without invoking a terminal. That reduces friction for adoption. It also means non-technical users may assume the interface is a sandbox when it is not. Shared state, shared memories, and shared credentials travel under the GUI. Convenience again trades off against control. If agents proliferate, control architecture matters more than prompt craft. There is a growing refrain in engineering teams: syntax is cheap, control is hard. You can prompt models into seemingly reliable outputs, but shaping the environment in which they operate is the scarce, expensive work. The argument often goes under the label context as code. The proposal is to shift constraints left, represent policy, interfaces and threat models in versioned artifacts, and test them as part of the build process. That suggestion is sensible. Treat context as an artifact you can test and version, not a string you paste into a request window. It is the software security principle applied to generative systems. Version constraints make behavior reproducible and auditable. They force cross-disciplinary judgment into the pipeline. But beware the paperwork trap. Contracts and tests do not magically make a model constraining, they make auditors feel better while the model still behaves unexpectedly. Controls are effective only when they are precise and enforced. Precision is also what separates a lab demonstration from a robust deployment when agents need to integrate with external systems. A small research team demonstrated an agent that writes its own adapters to connect to third-party APIs. The agent inspects a target service, produces the adapter code, scaffolds method signatures, and even writes tests. The idea is appealing because integration work is tedious and expensive. If agents can reliably generate connectors, teams could prototype faster and reduce the plumbing that stalls projects. The practical limits are immediate. Real APIs are messy. Auth flows, flaky endpoints, rate limits and undocumented behaviors remain a problem. An adapter that looks fine in a sandbox can fail under production load or handle sensitive data badly. Whoever or whatever generates the adapter also sets error handling and authorization semantics. You still need code review, provenance, and runtime guards. Automating responsibility does not eliminate responsibility. That runs straight into observability needs. 3 observability platforms were tested against common agent failure modes and the result was familiar, pretty visualizations and persistent blind spots. These tools can trace inputs to model calls, retrievals to tool actions, and flag cost spikes. They point to where the smoke is. They do not, by themselves, fix the leak. The hard work remains instrumenting the system with the right IDs and metrics. If you do not propagate context identifiers and relevance scores between components, the dashboards will show gaps. Telemetry costs money and affects latency. Sampling can hide rare but expensive failures. Traces can include sensitive data, and then trigger privacy questions. Observability helps only when it is designed as part of architecture, not bolted on afterwards. Those architectural questions are especially pressing in higher stakes domains. Health systems are watching agentic artificial intelligence with interest and caution. Agents that triage, coordinate tests, or schedule follow-ups could reclaim clinician time. But acting autonomously inside care pathways is different from presenting advice on a screen. It requires reliable data, clear objectives, and robust escalation mechanisms. It also rearranges accountability. If an agent orders the wrong test, who answers? The clinician who oversaw it, the hospital, or the vendor? The political economy in health is as important as the technology. Vendors who supply such agents control workflows and data flows. Procurement choices determine how interop and auditability evolve. Introducing agents without redesigning jobs risks offloading burden to the least powerful part of the chain, for example carers in the community. Technology can rehumanize care by removing drudgery, or it can bury compassion under new layers of complexity. Which it does depends on governance as much as on code. The governance theme returns in other arenas where provenance matters. A CARMS monitoring tool now surfaces the source as a model used to generate a claim. It is a practical product for PR teams that need to defend statements quickly. Showing where a model drew an assertion from speeds decision-making in a crisis and helps satisfy compliance demands. But provenance displays are not exhaustive. They do not expose entire training corpora. They make the process legible rather than transparent. Legibility has value. It is better to know a claim came from an obscure forum than to discover that after a board statement. Yet a provenance layer can create false confidence. Models can misattribute or omit private sources, and adversaries can gain signals through coordinated amplification. So treat provenance as a diagnostic tool, not a definitive audit. There is another democratizing current in the field that pulls in the opposite direction to centralization. A new Colab walkthrough packages a full pipeline for fine-tuning an open-source model using Clora and preference tuning. The notebook lets curious engineers run meaningful edits on cheap GPUs and experiment with behavior without buying racks of hardware. That lowers the barrier to meaningful model work. The techniques are powerful but delicate. Clora compresses weight updates to reduce memory. Preference tuning nudges the model toward outputs people prefer without building a big reward model. Merging adapters bakes modular edits into the main weights. These are neat engineering tools, and they let smaller teams iterate. But merging changes also makes rollbacks harder. Preference datasets matter enormously. Small changes to hyperparameters produce different outcomes. Running on Colab is not a guarantee of safety. Democratized tooling accelerates discovery and failure alike. It shifts where work happens and who pays for compute. That matters for power distribution as much as for innovation. Open licenses and lightweight tooling let more people experiment. They also make it easier to misuse or deploy poorly validated models. A parallel development is the arrival of encoder-free multimodal models released under permissive licenses. One recent model claims to process images and audio natively in a language backbone and to run on a laptop with 16 gigabytes of RAM. The promise is appealing: fewer moving parts, simpler pipelines, and the possibility of local inference that keeps private data on device. The reality is nuanced. Encoder-free designs can reduce integration complexity and latency. They also push representation learning into a single network that must learn to extract vision and audio features internally. To fit into modest memory budgets, developers use aggressive quantization and other optimizations. That will reduce fidelity and responsiveness. A model that produces outputs on a small laptop is not necessarily competitive with a larger, encoder-backed system running on a data center GPU. These developments matter because they shift deployment choices and raise familiar safety questions. Local inference reduces some cloud exposure, but increases device heterogeneity and the risk of stale weights. Open licenses make experimentation easier, but also reduce control over how models are used. The technical trade-offs are not ideological, they are practical ones about fidelity, latency and control. Robotics highlights yet another place where one-size-fits-all thinking fails. People building robots now argue that you need a stack of specialized datasets, not one monolithic corpus. Perception data, low-level control traces, instruction-following pairs and long-horizon episodic recordings are different beasts. They require different sampling rates, annotation practices and quality checks. Treating all data the same produces brittle agents that fail where it matters. Collecting those datasets is expensive and technical. Control traces require high-frequency synchronized logs. Long-horizon episodes demand careful episode boundaries and success criteria. Instruction data needs human judgments about intent. These tasks move budget toward data engineering, and away from headline model training. The labor shifts, and so do the contracts. Beyond robotics, there are moments where artificial intelligence contributes novelty rather than merely automating repetition. An internal language model produced what it and its patrons called a counterexample to a decade-old geometric conjecture. The claim was that the model had produced a concrete arrangement of points that violates a long-standing combinatorial bound. Well, that was another rather full-on week in the world of artificial intelligence. As ever, it's our aim here to sift through the noise and offer a modicum of clarity. If you find yourself wanting a more regular, perhaps even daily, digest of what's actually happening, rather than the weekly spectacle, you might consider the daily artificial intelligence briefing available at jonathanharris.online. It's a single email, free of undue excitement, just the facts. And for those of you who've been asking about my own contributions to the discourse, my book, Digital Defense: The Role of Artificial Intelligence in Modern Warfare, is available now. You'll find it in the ebooks section. That's your lot for this week's Turing's Torch. If you want the daily brief, head to jonathanharris.online. Same time next week. Try not to believe the press releases.